And in this part of our lesson, we're going to look at what's called the concavity of a function. And I think you'll find this isn't hard to do, but it's just an extension of what we do with our first derivative test. So let's jump in and take a look at what concavity is. It refers primarily to the shape of a graph. So if I'm talking about a graph being concave up, then on a particular graph, what's going to happen is you are going to see the graph open upwards towards quadrants 1 and 2. So it's going to have a bowl shape that looks like it opens upwards towards quadrants 1 and 2. And then by contrast, a graph that is concave down will have its bowl shape opening downwards towards quadrants 3 and 4. And you're going to find that a graph is concave up on an interval if its derivative is increasing, and concave down if its derivative is decreasing. Okay, now before we get too excitable about, thinking too hard about what that means, let's think about this part. If a function has a second derivative, then we can conclude that the first derivative increases when the second one is greater than 0 and decreases when the second one is less than 0. Alrighty. So the curve lies below tangents when it was concave down and above when it's concave up. An interesting little thing to kind of file in your back pocket for later when it comes to this idea of curve sketching. Okay, so the concavity test is very simple. The graph of a twice differentiable function f of x is concave up on any interval where f double prime of x is greater than 0 and concave down where f double prime of x is less than 0. Now that makes a lot of sense if you piece together what we've just talked about, but if following that's a little bit difficult, fortunately for you, this is a pretty easy thing to remember. Concave up when the second derivative positive, concave down when it's negative. Just that easy to do. All right, let's take a look at how we would determine concavity. Start with something pretty simple like the graph of y is equal to x squared on the interval from 3 to 10. Well, you're going to need the second derivative, and dy over dx is going to be 2x, and then the second derivative is just going to be 2. Well, normally we would do something pretty similar to a sign chart, but we don't have to worry about that for this particular example because our second derivative here is always, let me make that arrow a little bit better, positive. So the graph is always concave up, and that makes a lot of sense for that particular scenario. All right, let's take a look at this other one. Trig functions, they bounce around a lot, so here's a good chance for us to look at this. Our dy over dx for this one is going to be cosine because the 3 just drops out. And then our second derivative is going to be negative sine of x. Okay, probably not a bad plan to think about where the sine is 0. And on an interval from 0 to 2 pi, there's only one other place where the derivative is 0, and that is at 0 itself. The second derivative, that is. And it's helpful if we just kind of remember that this is our y double prime, our second derivative. And if I pick values that are both negative and positive, I can sort of find my way around here. Oh, why did I write 0 there? I have no idea. Boy, I'm just kind of really being a little bit scatterbrained with this. Good heavens. Maybe that calls for another booing. I don't know. See what you think about that. Well, that won't go away then, maybe. There it goes. All right, so here is my pi, actually. That's what I meant to write. Why did I write 0? Must have had 0 on the brain. Okay, so if I pick a value between 0 and pi, let's just pick something like pi over 2. If I put that into my second derivative, sine of pi over 2 is 1, but then there's that negative out in front. So it's going to be negative. And then if I pick like something between pi and 2 pi, like, I don't know, 3 pi over 2, for example, sine of 3 pi over 2 is negative 1, but then the negative sign forces it to be positive. So now I know this graph is concave down from 0 to pi and concave up from pi to 2 pi. I know that for sure. Okay, good information to know on those two particular functions. Okay, now the big question sometimes becomes, what is this idea of a point of inflection? A point of inflection is where the function has a tangent line, but the concavity changes. Interesting. Okay, so the derivative exists and the function is continuous, and where the concavity changes. So if you have, like, for example, the sine function, let's just kind of use that one because it's a pretty easy function to work with here. If you go ahead and make your graph of the sine function, you will notice that at this particular point right here, it almost sort of inverts itself and goes from concave down to concave up. It's really fascinating how that works. And if this were to continue, you'd see the same pattern over and over again, of course. All right, so what we're looking for on a point of inflection is where the concavity changes. All right, now the second derivative need not exist, but the first one probably should. So that's good information to know. All right, let's find all the points of inflection for this graph of y is equal to e to the negative x squared. Oh, this is going to be a little sinister here. Let's start with the derivative first. And the derivative is going to be e to the negative x squared times negative 2x, because that's the derivative of the inner function for the chain rule. All right, now we've got to do product rule for the second derivative. Make anybody scream for sure. So let's go ahead and do our product rule. Our u prime is going to be e to the negative x squared times negative 2x. And then our v is negative 2x, of course. And then let's see, we were going to have just negative 2 there. All right, now you remember the trick in the previous video that we talked about. It's helpful if you just factor out your e to make this a little bit easier. So that's what I'm going to do, e to the negative x squared, and this is going to give me 4x squared minus 2 when it comes to simplifying and combining and factoring out. All right, now if I go to find out where this is going to be 0, anything that's got an e on it, I already know that's going to be positive, so I don't have to worry anything about that. But this I have to worry about. And I'm going to go ahead and tell you that this is going to end up being x is equal to plus or minus root 2 over 2 when you set this particular part, what's in the parentheses, equal to 0 and solve it out. All right, so now I can know where my so-called critical points are. Now I can make my sign chart on my second derivative at negative root 2 over 2 and positive root 2 over 2. All right, probably good to pick something simple to work with here. Let's go ahead and pick 0. And if I pick x is equal to 0, a value in the middle, whoopsies, let's get the right tool here so you can actually read it. Okay, so if I pick x is equal to 0, then I'm going to end up with something that's negative. And if I pick x is equal to 1, that's going to definitely be greater than root 2 over 2. And I put that value again in here in the second derivative. That should give me something that's positive. And for x is equal to negative 1, it's also going to give me something that's positive. So what we're looking for, remember, is a change in concavity. And we have that change in concavity at both of these values. At this first one, negative root 2 over 2, it goes from positive to negative, and then this goes from negative to positive at positive root 2 over 2. So we can make the conclusion that both of these are points of inflection. Okay? But again, the key thing is where the concavity changes. That has got to be a huge thing to consider here. Last point I want to raise on this is that we've got to be cautious. Okay? It's really tempting to oversimplify and just say, oh, this is where the second derivative is 0, but that can be wrong for two reasons. The second derivative could be 0 at a non-inflection point. If you were to graph x to the fourth, you'd find out that the second derivative of that at 0 is 0. But it's not an inflection point. It's an absolute min, so something to think about there. Second derivative need not be 0 at an inflection point itself. Consider the cube root of x. You're going to have a vertical tangent there. Even though both f and f prime fail to exist, there is a change in concavity. So the safest way to test for a point of inflection is to confirm that there was a sign change in the second derivative. This could occur at a point where the second derivative is 0, but it could also occur at a point where the second derivative fails to exist. So I know I've emphasized that change in concavity several times already, but that just kind of reinforces the point. All right, very good, and enjoy.